Good afternoon, dear students. Today we continue with our module of fundamental physics, still in part 1 of classical and fluid mechanics. Unit 5, kinematics of rotational motion. In theory, we described rotational variables, rotation with constant angular acceleration, relationship between linear and angular variables, kinetic energy of rotation, and the moment of inertia. Today we need to continue with exercises about rotational motion. Exercise number 1. Statement. The angular position of a point on the rim of a rotating wheel is given by theta equals 4t minus 3t squared plus t to power 3, where theta is in radians and t is given in seconds. Asked, what are the angular velocities at t equals 2 seconds and t equals 4 seconds? B. What is the average angular acceleration for the time interval that begins at t equals 2 seconds and ends at t equals 4 seconds? What are the instantaneous angular acceleration at the beginning and end of this time interval? Here we need to work together in order to find an answer. We are given the expression of theta as the angular position. Theta is expressed in terms of time, where theta is in radians and the time t is in second. Now, to find the angular velocity, we need to use definition. The first definition for angular velocity states that the angular velocity omega equals to the first derivative of angular position with respect to the time. This is equal to derivative with respect to the time of the expression theta equals 4t minus 3t squared plus t to power 3. We know the formula for derivatives. Everyone knows how to derive. We know that d of a function x to power n with respect to x, this is equal to what? This is equal to n times x to power n minus 1. And this is the general formula for derivatives. We are going to apply this formula to our problem. And then you will see that the angular velocity will be equal to 4 minus 6t plus 3t squared. Here where t will become, it has a power 1. 1 times 4 gives 4. T to power 1 minus 1 gives t to power 0. Then any number to power 0 gives 0. Here we have 2 times 3 gives 6. 2 minus 1 gives 1. Then here we have 3 times 1 gives 3, and the power is 3 minus 1, which is 2, where the expression of angular velocity equals 4 minus 6t plus 3t squared. We are asked to determine the angular velocity when the time t is equal to 2 seconds and the time t equals 4 seconds. Here we need to find the value of omega when the time t equals 2 seconds. We need to replace t by 2. Then omega 1 when the time t 1 is equal to 2 seconds equals 4 minus 6 times 2 plus 3 times 2 squared. This is expressed in radian per second as the unit of angular velocity. The answer is 4 radians per second. Omega 2 is the value of omega, means a value of angular velocity when the time t equals 4 seconds. This is equal to 4 minus 6 times 4 plus 3 times 4 squared. 4 squared is equal to 16. 16 times 3 equals 48. 48 minus 24 equals 24. 24 plus 4 equals 28. Then omega is expressed in radians per second. In sub-question B, we are asked to determine the average angular acceleration. By definition, the average angular acceleration is denoted by the letter alpha with index AV, which is equal to the change in angular velocity over the time interval. This delta omega equals the second or the final angular velocity minus initial angular velocity divided by final time minus initial time. Here it is said that the time changes from 2 seconds to 4 seconds. Then time equals to seconds is time t1, which is the initial time, and the time t equals 4 seconds is the final time or time t2. And we need to replace each value by we need to replace each quantity by its value. Omega 1 is calculated to be 4 radians per second. Omega 2, 28 radians per second. Time t1 equals 2 seconds. Time t2 equals 4 seconds. Then we need to replace each variable by its value. Then we have average angular acceleration to be 28 radian per second minus 4 radian per second over 4 seconds minus 2 seconds, which is equal to 24 radians per second divided by 2 seconds. Then the final answer for average angular acceleration is 12 radian per second squared. In number C, we are asked to determine the instantaneous angular acceleration at the beginning and the end of this time interval. The beginning of this time interval is time t1, which is equal to 2 seconds. And the end, this is the beginning of the motion. Beginning. Then this is the starting point of the motion, and the time t2 equals 4 seconds, which is the ending point of the motion. This is an ending point or ending time, ending point of the motion. Then we are asked to determine, first of all, the expression for instantaneous angular acceleration. By definition, the angular acceleration or instantaneous angular acceleration is given by alpha equals the first derivative of angular velocity with respect to the time, which is equal to the first derivative with respect to the time of the expression that we have found here is omega equals 4 minus 6t plus 3 times t squared. Then, according to this formula for derivatives, derivative of any function with x to power n with respect to x equals n, the power of x, times x to power n minus 1. The derivative of a constant gives 0. It's the reason why the derivative of 4 becomes 0. Then this derivative will be equal to minus 6 plus 6t. And we are asked to determine the instantaneous acceleration at the beginning and the end of the time interval. Beginning of this time interval is when the time t equals t1. Then alpha 1 equals alpha when time t equals 2 seconds. We need to replace the time t by 2 into the expression for instantaneous angular acceleration. This is equal to minus 6 plus 6 times 2. This is equal to minus 6 plus 12 equals 6 radian per second. Radian per second is the unit of angular acceleration. Then we are asked to find instantaneous angular acceleration at the end point of the interval. The end point is when the time t equals 4 seconds. Now we need to find alpha 2, which is equal to the value of alpha when the time t equals 4 seconds. we need to replace t by 4 in this expression for instantaneous angular acceleration. Then equals minus 6 plus 6 times 4. 6 times 4 equals 24. 24 minus 6 equals 18. Then the final instantaneous angular acceleration equals 18 radian per second squared. Question number 2. Statement. An astronaut is being tested in a centrifuge. The centrifuge has a radius of 10 meters and in starting rotates according to equation theta equals 0.30 t squared, where t is expressed in seconds and theta is in radians. When the time t equals 5 seconds, what are the astronauts' A. Angular velocity, linear speed, tangential acceleration, only magnitude, and the radial acceleration? Here you can add the value of the total acceleration of this centrifuge. A centrifuge is any device which has a rotating part inside it. The centrifuge machine is actually used in chemistry. You will meet it during your chemistry laboratory activities in order to separate water from chemicals. As an answer, we need first of all to state what is given, all of the data. It is said the centrifuge has a radius of 10 meters. We have a radius 10 meters. Then we are given angle, an angle that this centrifuge rotates. This angle is the angular position theta equals 0.30 t squared. And the time, it is said at time t equals 5 seconds, determine the following. We are given the time equals 5 seconds. The asked in A, we are asked to determine the angular velocity of the centrifuge. The angular velocity is given by the general expression that angular velocity is equal to the first derivative of angular position with respect to the time. As we are given the angular position as 0.3 times t squared, this is derivative of with respect to the time t of the expression 0.3 t squared. This is equal to times 0.3 t. We refer to the previous question about the formula for derivatives. We know that the derivatives of any function x to power n with respect to the variable x is equal to the power n times our variable x to power n minus 1. It's the reason why in derivatives we have 2 times 0.3. 2 is the power of t. And the remaining t will have a power 2 minus 1. Then t to power 1. And we see that omega, which is the angular velocity, has an expression in the function of time of 0.6 times t. We are asked to determine the angular velocity when the time t equals 5 seconds. This means that when in expression for angular velocity, we need to replace the time t by its value, which is 5. Then omega when the time t equals 5 seconds is equal to 0.60 times 5 radians per second. This is equal to 3 radians per second. In sub-question B, we are asked to determine the linear speed. The linear speed has a relationship with angular speed, where the linear speed v is equal to the radius times the angular speed. Here, the radius is given to be 10 meters. The angular velocity at time t equals 5 seconds is calculated to be 3 radians per second. Then we need to replace r and omega by their values. Then v equals 10 meters times the 3 radians per second, which is equal to 30 meters per second. Here we have a meter times the radian per second, and the answer becomes meter per second. You may ask me why I didn't incorporate radian in the final result. Here, when meter is multiplied by radian, the result becomes meter. When you multiply meter and radian, the result becomes meter. This is a fundamental convention. Then number C, we are asked to determine the tangential acceleration, magnitude only. The tangential acceleration is given by the expression that A with index t equals to the radius times the angular acceleration, alpha. Then we know that the angular acceleration is equal to the first derivative of angular velocity with respect to the time. Then we need to find the angular acceleration, which is equal to the first derivative with respect to the time of the expression 0.6 times t, which is an expression of our angular velocity. Then we need to derive this, and it becomes 0.6 radian per second squared. As the first derivative of angular velocity becomes a constant, this means that this angular velocity is a constant at all times. It doesn't change. And then we need to go back to our expression for the tangential acceleration. Tangential acceleration is equal to radius times the angular acceleration, which is equal to 10 meter, which is the radius, times the angular acceleration is 0.6 radian per second squared. In a similar way, when you take meter and you multiply by radian, the answer is automatically meter. And then this tangential component of acceleration becomes 60 meter per second squared. In subquestion D, we are asked to determine the radial acceleration. The radial acceleration is the normal acceleration or centripetal acceleration. A centripetal acceleration is an acceleration which makes a body to maintain its circular trajectory. Let us consider a rigid body like this, and this rigid body is in x and y Cartesian plane. Let us consider a point P of the rigid body. If this rigid body is allowed to rotate in a counterclockwise direction, this point P will take a circular trajectory and it will have a radius r. This is the radius r of this circular trajectory. And then, so let us plot this circle in the right way. Then we need to make this circle clean. Then this particle will undergo a circular trajectory, make a circular motion approximately like this. Then this is the radius r, and the particle here has an acceleration which has two components. There is a component tangent to the curve, which is the tangential acceleration at, and there is another component which is oriented towards the axis of rotation, means the center of the circle. This tangent is called radial acceleration because it is oriented towards the radius, or also called the normal acceleration A with index n. Normal acceleration means centripetal acceleration. The centripetal acceleration is an acceleration which allows the body to maintain a circular trajectory. Then this is a vector quantity. At is a vector quantity and AR is a vector quantity. And the two vectors have the same origin, which is this point here. And then we know that how to add the vectors with the same origin. We use the parallelogram method. Let us find the parallel of AR starting from the tip of AT. use a broken line. And let us find a parallel to AT starting from the tip of AR. The two vectors meet at this point. And then we need to plot a diagonal. This diagonal becomes the acceleration A. This is the total acceleration of such particle of the rigid body in rotation. Then this radial acceleration is equal to the square of linear speed divided by the radius. The linear speed is calculated to be 30 meters per second, and the radius is given to be 10 meters. Then you take 30 meters per second squared divided by 10 meters. This is equal to 900 divided by 10, which is equal to 90 meters per second. And I may add subquestion E. Subquestion E, you may be asked, find the final acceleration A. Find acceleration A. Find acceleration. Yeah, we know that the acceleration is equal to tangential acceleration plus radial acceleration here, according to the diagram. And then to find the magnitude of such vector quantity, we take the square root of tangential acceleration squared plus radial acceleration squared, which is equal to square root of 60 meters per second, which is the tangential acceleration, plus 90 meters per second squared, which is equal to radial acceleration. And the final answer for the acceleration of such centrifuge is 108 meters per second squared. We can move to question number 3. Question number 3 states that calculate the rotational inertia. Here, the rotational inertia is what we have seen as the moment of inertia I. This is what you call moment of inertia. In other terms, it's called the rotational inertia, especially in engineering mechanics. People in civil engineering need to use, or civil engineers use the term rotational inertia, moment of inertia. And then the moment of inertia of a wheel. We are given a wheel. This is another important data. A wheel has a shape of a disc. Then, and a disc has a shape of a solid cylinder. This is a solid cylinder. This is a solid cylinder. This is a solid cylinder. And we know how to calculate the moment of inertia of a solid cylinder. The moment of inertia of a solid cylinder is equal to 1/2 mass of the cylinder, or mass of the disc, times the square of radius. Then if the mass is given, you may calculate, and the moment of inertia is given, you may calculate the radius. If mass and the radius are given, you may calculate the moment of inertia. And we are given that the kinetic energy is equal to 24,400 joules when it is rotating, when the wheel is rotating at 602 revolutions per minute. As an answer, we first write down the data. The first data is the wheel. As I stated, a wheel is having a form of a disc. A disc is considered as a solid cylinder. And here we need to write the moment of inertia of a solid cylinder or a disc. Then we are given another data, which is the kinetic energy of rotation. Kinetic energy of rotation 24,400 joules. And we are given the angular velocity 602 revolutions per minute. Here we are given the angular velocity in revolutions per minute, which is not the SI unit of angular velocity. Then since the SI unit of angular velocity is radian per second, we need to convert revolutions per minute into radians per second. How do we perform calculations to convert revolutions per minute into radian per second? We need to find an equivalencies between revolutions into radians and the equivalence of 1 minute into seconds. We have 602 revolutions per minute. Then we need to find an equivalence of 1 revolution. It's the reason why we need to multiply a term which has revolution in the denominator. Then we need to find its equivalence at the numerator. Then 1 revolution is equal to pi radians, because once you have a circular motion, an angle around a circle is 360 degrees, and these 360 degrees are equal to an angle of 2 pi radians. 2 pi radians. And if a body makes a complete revolution, it means that the body makes a complete circle. If the body makes a complete circle, it moves an angle theta, which is equal to 360 degrees, which is equal to 2 pi radians. This means that one complete revolution is equal to 2 pi radians. It's the reason why we say that an equivalence of 1 revolution is equal to pi radians. And here revolution at the denominator will simplify with revolution at the numerator. It will remain radian per minute. We need to eliminate minute by multiplying minute to the numerator. Then 1 minute is equal to 60 seconds. It's the reason why this minute at the numerator simplifies with minute at the denominator. And the final answer will be radian divided by second. This is the final answer. It's the reason why we take 602 times 2 times 3.14, because pi is equal to 3.14. And then divided by 60 seconds, and the answer is approximately 63 radian per second. Then we are not done. Remember, we are asked to determine the moment of inertia, which is the rotational inertia, and we are given the kinetic energy of rotation and the angular velocity. We know the formula. The kinetic energy of rotation is equal to the half of the product of moment of inertia and the square of angular velocity. Then this kinetic energy is given, the angular velocity is given and converted into radian per second. The unknown here is the moment of inertia. Then we need to rearrange this formula in order to determine the moment of inertia. By multiplying 2 in both sides of this equality, we have a 2 times kinetic energy of rotation equals moment of inertia times the square of angular velocity. Then we will see that the moment of inertia becomes 2 times kinetic energy of rotation divided by the square of angular velocity. We may do the numerical calculations. 2 times 24,400 joules divided by 63 radian per second. Then this is squared, which gives 12.3 kilogram meter per second. Why we say that the unit of the moment of inertia is kilogram meter per second squared? It's because actually the moment of inertia is said to be equal to the sum of the product of masses mi times the square of the distances. This is a distance r squared, and we know that the mass is expressed in kilogram, and any distance has an SI unit, which is meter squared. Then this is expressed in kilogram, and the distance is expressed in meters, and we have a distance squared. So the reason why the moment of inertia has a unit kilogram meter squared. Question number 4. We are given a challenging question here to calculate the rotational inertia, means moment of inertia of a meter stick with a mass 0.56 kilogram about an axis perpendicular to the stick and located at the 20 centimeter mark. We have a 1 meter stick. This is a 0 mark, and here we have a 20 mark, 40 mark, 60, 80, and 100 mark. These marks are given in centimeter, and we know that the stick has a length of 1 meter, and we know that 1 meter is equal to 100 centimeters. Is equal to 100 centimeters, and it's the reason why we need to plot our stick from having dimensions from 10 to 100 in centimeters. Here the middle is the sticker is a uniform rod or a uniform object. Then the center of mass means where the point where all the mass of the stick is concentrated is called the center of mass. Then it will be at a 50 centimeter mark. And here we may consider a distance from the center of mark to the point where the axis of rotation is located. This is distance, let us call it D. And here comes a fundamental principle which is called the parallel axis theorem. This is called the parallel axis theorem. The parallel axis theorem states that if we have a point P here, there is a moment of inertia about point P and a moment of inertia about the center of mass. Then the moment of inertia about point P means a moment of inertia about a parallel axis to the principal axis, means the principal axis of rotation would pass through the center of mass. Here there is a principal axis of rotation, PA. Then this is equal to the moment of inertia about the center of mass plus the mass of the rigid body, means the rotating body, times the square of the distance D, which is between this new axis and the axis passing through the center of mass. As shown here in the answer, we are by using the parallel axis theorem, the moment of inertia to the parallel axis is equal to the moment of inertia about the center of mass plus mass times d squared. Here the mass is given to be 0.56 kilograms. Let us be 0.6. Let us say 0.5. Then the ICM means the moment of inertia about an axis of rotation through the center of mass. And here this ICM equals 1/12 meter mass times the square of the length. L is the length of the stick. And here the moment of inertia is equal to this. Remember what we have seen in theory. Moment of inertia of a uniform rod when the axis of rotation passes through its center of mass equals 1/12 mass times the square of the length of the rod. D is distance between the point P here, this point where the new axis of rotation passes, and the center of mass. Cm means center of mass. And then we have IP equals 1/12 mass times the square of the length. The square of the length is 100 centimeter, which is equal to 1 meter, and plus the product of mass and d squared. D is given to be 30 centimeters. The distance from 20 to 50 is 30 centimeters. 30 centimeters are equal to how many meters? 0.3 meters. It's the reason why here in numerical calculation we consider the IP equals 1/12 times 0.5 times 1 squared plus 0.5 times 0.3 squared, which gives approximately 0.087 kilogram meter squared. We can move to question number 5. We are given a machine part which consists of 3 discs. We have a disc A with mass 0.3 kilogram, disc B with mass 0.1 kilogram, disc C with mass 0.2 kilogram. The distance between disc A and disc B is 0.5 meters. Distance between B and C 0.3 meters. Distance between A and C are 0.4 meters. It is given that there is an axis of rotation through disc A and another axis of rotation which passes through the centers of disc B and A. This means that this part or this machine can rotate about point A. In the same time, this machine can rotate about this axis passing through B and C. If it rotates here, it may rotate either in clockwise direction or in counterclockwise direction. If it rotates about this axis, it may rotate about this axis in counterclockwise direction, or it may rotate in clockwise direction. Let us read the statement. A machine part consists of 3 discs linked by lightweight struts. A. What is this body's moment of inertia about an axis through the centers of disc A? We are asked to find the moment of inertia about disc A. B. This perpendicular to the plane of the diagram. B. This is sub-question A. Moment of inertia about A. B. What is the moment of inertia about an axis through the centers of disc B, C? There is another moment of inertia about an axis passing through the centers of discs B and C. This is equal to what? This is sub-question B. Then in sub-question C, we are asked to determine the body's kinetic energy if it rotates about an axis through A. Means the kinetic energy of rotation by considering the axis of rotation through A. This would be the moment of inertia about A times the square of angular velocity, then divided by 2. And we are given that the angular velocity equals 4 radian per second. As an answer, we need first of all write down the formula. The moment of inertia is equal to the sum of masses, the product of masses, and the square of distances. Here we have 3 discs. There is disc A, disc B, and disc C. There is one body is disc A. Distance, mass A times distance of A from A squared plus mass B times the distance AB squared plus mass C times distance AC squared. Then this is equal to 0 plus 0.1 times 0.5 squared plus 0.2 times 0.4 squared. This gives 0.057 kilogram meter per meter squared. Then number B, we are asked to find the moment of inertia about an axis through the centers of B and C. We have this center. We have this axis of rotation. If the axis of rotation passes through disk B doesn't rotate. If the axis of rotation passes through disk C, then disk C doesn't rotate. So the distance between B and the axis of rotation becomes 0. It's the reason why we have this distance RBB is equal to 0. And the distance between C and axis of rotation is equal to 0. It's the reason why you have distance RCC equal to 0. But here only disk A will rotate about an axis through BC. If AB rotates, we need to consider the shortest distance between disk A and the axis BC. The shortest distance between A and BC is 0.40 meters. It's the reason why here we have multiplied 0.3 kilogram as the mass of A times 0.3 meter squared is the shortest distance between A and the axis BC. Then this moment of inertia becomes 0.048 kilogram meter squared. In sub-question C, we are asked to find the rotational kinetic energy about A equals 1/2 times the moment of inertia at about A times the square of angular velocity. Moment of inertia about A is calculated in sub-question A, and the angular velocity is given. So we need to do the numerical application, and this rotational kinetic energy is equal to 1/2 times 0.057 kilogram meter squared times 4 radian per second squared, which gives 0.456 joules. And we are finishing, left only one question. This question is a bit similar to the previous questions, and we need to answer to it as quick as possible. Statement: a wheel rotates with a constant angular acceleration of 3.5 radian per second squared. This is the angular acceleration. If the angular speed of the wheel is 2 radian per second when the time t is equal to 0, we are asked through what angle. This angle means angular position. Angular position. Angular position is theta. Angular position denoted by theta. When the time t is equal to seconds, we are asked to find the angular speed when the time t is still 2 seconds. We are asked to find the angle through which this angle that the wheel rotates when the time changes from t1 equals 2 seconds to t2 equals 3 seconds. This is delta theta, which is angular displacement. As an answer, we are given in our data angular acceleration 3.5 radian per second squared, initial angular velocity, because this is an angular velocity when the time t is equal to 0. This means that this angular velocity we have here is initial angular velocity. This angular means angular velocity at time t, at initial time. This is the initial angular velocity. Omega 0 equals 2 radian per second when your initial time t0 is equal to 0. Then we are given that the time t, the final time equals 2. We are asked to find the angle through which the wheel rotates, which is the angular position. By definition, theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. Theta 0 is 0 because at because it is not given. If it is given, we will use it. Then plus omega 0 equals 2 times 2 times the time t is equal to plus 1 over 2 times 3.5 times 2 squared. This gives 11 radians. Then in number B, we are asked to find the angular speed. The angular speed is equal to omega plus omega 0, omega equals omega 0 plus alpha t. Omega 0 is given, alpha is given, and the time t is given. We need to replace each variable by its value. Then omega equals 2 radians per second plus 3.5 radians per second squared times 2 seconds, which is equal to 9 radians per second, because 2 times 3.5 equals 7, 7 plus 2 equals 9 radians per second. Then number C, angular displacement between t1 equals 2 seconds and t2 equals 3 seconds. Delta t here equals t2 minus t1 equals 3 seconds minus 2 seconds equals 1 second, and delta theta equals theta 2 minus theta 1, where theta 2 is the angular position when time t equals 3 seconds, the time number 2, because theta 0 plus omega 0 t plus 1 over 2 alpha t squared, where t will be replaced by 3, omega 0 2, theta 0 equals 0, and we see that theta 2 equals 21.75 radians, and theta 1 equals theta when the time t equals 2 seconds. In the sub-question A, we have calculated the theta when the time t equals 2 seconds, so theta 1 equals 11 radians per second. Then the angular displacement delta theta equals theta 2 minus theta 1 equals 21.75 radians minus 11 radians, which is equal to 10.75 radians, and we are done. Thank you very much for